Recording. Fine. Okay, so good evening again. This is week 11 of Introduction to Semiconductor Fundamentals. And today we have reached to the level where we can basically discuss the application part of the of in this course, which are the photodetectors and the solar cells. And I'm Shazam, but I'm a direct PhD student at IIT Bombay. And this course is being offered by Professor Naresh Imani and in collaboration with IIT Madras and IIT Hyderabad. So, what we are going to do today is to study about certain optical, I should say, devices which are used in the state-of-the-art industries. Let's say solar cells, photodiodes, photovoltaics, basically, and photodetectors. They are just the backbone of our communication systems, as well as all of the detection systems, whether it's used in industries or commercial applications, defense applications, or tactical applications, even in day-to-day applications, they are being used. And we're briefly going to discuss about it. So I'm not sure whether my video is visible or not, but there is some issue with my camera today, so maybe it's not visible. So let's get started. So what we are going to cover today is what will be the outline of today's session. The outline of today's session is going to be we are going to study about uh, optical absorption methods. We are going to start about optical absorption techniques, and we are going to study about direct and indirect bandgap semiconductors. Indirect bandgap semiconductors. We're going to study about electronic transitions, how the electrons respond to the incoming light, electronic transitions, and this will pave the way for understanding certain devices, let's say photodiodes, let's say we have the solar cells, we have photo detectors, which is basically a photodiode. We have maybe some other kind of devices we will study, maybe avalanche diode and other, I should say, complex devices if the time permits. And then we are going to move into the equation part of it, how the generation recombination takes place in it, and what are the governing equations behind it. So let's get started directly with what we are going to cover today. Okay, and a brief recap is necessary for what we covered in the last classes. Okay, so a brief recap about what we covered till last class. So till now, what we have studied is we have basically, if we see the overview of this course, what we have learned and where we have reached. You remember if you remember we started with atoms and we draw its potential diagram, which is which is the potential felt by the electrons. Okay, this is the potential felt by the electrons. Then you see these overlapping regions. This is where actually the this gives rise to a band gap because there are two overlapping potentials and you cannot electron cannot have a potential in this particular value because there are two different potential values here. So when you draw the band diagram, you draw it something approximately like this. And in the band structure, it gives rise to gap opening, which you might have seen from the this particular figure, which is in the first Brillouin zone. So this is the band gap opening. So that is just the overview what we studied. And from this picture, we studied about the chronic Penny model. We went into the Bloch's theorem, which discussed about the periodicity. Then we directly studied about the band structure, which is basically the EK diagram, which is basically the band structure, which is the E versus the electron momentum, which looks something like this. If you know that looks something like this, which is the extended zone representation. Extended zone representation. And this is E, this is K. And when you fold these bands back into the first zone, which is something called as Brillouin zone, you get a region which looks something like this, where you have these bands folded in the first zone, and you call these as energy states, which are the acceptable energy values of an electron in the K space. Okay, these are the energy acceptable values, and you call the lowest of this as conduction band, the highest of this is valence band, and this is the energy gap of the for the electron, which is the forbidden energy gap. Then you moved from this band structure and you studied about the carrier electrostatics. Carrier electrostatics. The reason why I'm going back to all this is because all this is going to be useful in today's lecture. Whatever the application part is, it is just the manifestation of what you have studied till now, starting from the basic electrostatics. All of those equations, maybe whether it's about the p-n junction diode, whether it's about the electrostatics, that is going to be useful in today's lecture. So just let me use the charger. So that is what we are going to study today. And if you see, then later on, where we moved is in carrier electrostatics. You studied about the drift, you studied about the diffusion, you studied about the Poisson equation. Poisson equation. Using these, you studied about how you can get the band diagram of any structure, any semiconducting structure, and you know that drift, diffusion, and Poisson equation. You know, if there is an electric field present, then there is an there is electron drift and the hole drift. In presence of the electric field and the you see the drift current, because of that particular drift of the electron due to the drift velocity, which is proportional to this particular thing. The drift velocity is proportional to the electric field, and mobility is a proportionality constant here. And you have the drift current because of it, which is equivalent to q times mu n times the Qn times the I should say drift velocity, and you can write it as Qn times the mobility times the electric field, which is the drift current density of the electrons. Similarly, you can write the drift current density for the holes. But this is P, the charge remains same. So N and P are the concentrations of the electrons and the holes. This all you have covered in the previous lectures already. Similarly, for the diffusion, using the Fick's law of diffusion, diffusion is applicable to all of the scenarios, whether it's a fluid diffusing, whether it's water, whether it's any flowing medium. So you use the diffusion law, diffusion equation, and you get the current because of the diffusion is equivalent to q dn by dx, and because of the this is electron current, this is the hole current, that is equivalent to this particular thing. It is equivalent to the gradient of that particular, basically the concentration gradient in space. So that gives you the diffusion and the drift components. And when you combine all of those, you get the total current inside the device, which is the drift current, which is the drift part plus the diffusion part. And each of those has its own whole electron component, hole component, electron component, and the hole component. And then you studied about the Poisson equation. The Poisson equation is basically the this particular thing. If you can write in terms of the potential, it gives you something like this, which is the dou square potential. V is the potential divided by dou x square is basically the density charge density in per centimeter cube divided by the permittivity of the medium. Similarly, you can write this thing as using in only one coordinate, I should say in one dimension. You can write it something like this, because the dou v over dou x is equivalent to the electric field. Okay, so these equations are necessary in order to understand the carrier electrostatics inside the device, what you have studied till now. Now, you studied about the p-n junction diode. You studied about what you had studied is that if this is the band diagram of a p-n junction, this is the p side, this is the n side, and this here is something called as depletion region, where this is the depletion width, and you have the positive ions here, which are the immobile ions, assuming that both P and N side are equally doped. They are equally doped. So the depletion region will look something like this. In the middle, this will look something like this. These are the immobile, I should say, ions present. And because you have a positive ion and an electron here, you have a negative ion and a hole here. So the electron will go onto this side, the hole will go onto this side. The remaining things are these positive and negative things, which basically come at this position whenever the I should say two materials are combined. So this diffusion or depletion layer forms whenever the two materials are combined. Whenever there's a junction between the two materials of different doping densities as well as two different materials of different characteristics. So you get this particular depletion region. And now you see that there is a built-in electric field setup which the electric field emanates electric field line comes out from a positive charge, ends on a negative charge. So you have an electric field in this direction. If you have a positive charge, you have a negative charge. Electric field comes from a positive charge and ends on a negative charge. So these are the electric field lines basically, which look something like this. So these are the electric field lines coming out of a positive charge and ending on a negative charge. Okay, and you know the all of the equations for the built-in field. You know the built-in electric field. You know the built-in potential. You know the equations for the depletion width of a device, which is approximately twice epsilon by q, 1 over the doping on p side divided by 1 over doping on n side. V built-in plus minus V applied, where this V applied can be either a reverse biased voltage, it can be a forward biased voltage. So accordingly, you have to take the sign. And if you have the forward voltage, you get a decrease in the depletion width. If you have the reverse voltage, you get increase in the depletion width, because this will be minus because of the, I should say, lowering of the band, because of the lowering of this middle hill in the forward region, and as a result the current flows and you get a reduction in the depletion width in the forward region. Okay, so that you have covered till now. So what is the case today? What is basically the scenario going to be today? Now you know anything which is going to be, let's say, because of the built-in electric field, if you do something to this particular scenario, let's say you have this particular device and you brought external something perturbation, something called as perturb. You perturb the medium. This can be anything, maybe let's say heat, let's say light, or let's say any other external disturbance to this particular system. What is it going to do is that it's going to generate the electron hole pairs. Let's say, for example, in the depletion region an electron hole pair gets generated. We are just assuming it's getting generated in the depletion region. It can happen throughout. Electron hole pair can be generated here, electron hole pair can get generated here, it can get generated at this particular position. Now what is going to happen? If you have, let's say, an electron hole pair generated at this particular position, because of the internal electric field, this electron will feel the force opposite to that of the electric field, because F equals to minus Q times E. So this electron will go in this direction and this hole will go in this direction. Because of the electron going in the right direction, the current will flow in this direction, which is the electron current, IE, and because of the hole going towards left direction, the whole current will flow in this direction, which is the IH. So overall, you will be having a current towards this direction, which is the total current, which is electron current plus hole current. So you see what happened is that there is a current flow because of the generation of the electron hole pairs inside the device. If you perturb it, now what is that perturb? Perturb means any disturbance that can generate electron hole pairs. The key fundamental thing is electron hole pair should be generated. Now it cannot happen only in the depletion region. It happens throughout. How do we control it and how do we make sure that we separate these electron hole pairs is the fundamental thing about this today's session, and how the actually the engineering is done in order to ensure that these particular electron hole pair get separated without the application of the external bias. You are separating those electron hole pairs, and that is resulting in the flow of the current, and that is the fundamental of the solar cell basically. That is the fundamental of the solar cell. So that is what we are going to study today. And now there are a few things. Let's say you have a semiconductor chunk. Let's say you have a semiconductor, any semiconductor. It's not only about semiconductor. If you take any material, be it a metal, be it an insulator, be it a semiconductor. These are the three categories of the materials we have. There is a minimum, I should say, distance up to which a light can penetrate inside the medium, and that particularly depends upon the band gap of the material. That depends upon the and definitely band gap determines what sort of wavelengths will be absorbed. So if you, let's say, have a light source, and if you shine a light source from this side, which is, let's say, some light beam coming from this side, and this, if this is the x distance, if this is the x coordinate, x dimension, then you will see that this particular light will exponentially decay inside the medium. And what will this decay depend upon? It will depend upon a coefficient which is something called as alpha. This alpha is called as absorption coefficient. Absorption coefficient. Okay. And it may so happen that light will diffuse like this inside the medium and come out through the other end. It may so happen that it can go like this and come out through the other end. But it may so happen that light may be exponentially decay and get absorbed inside the medium, or absorbed up to this depth. So what this depth is, basically this particular region, this particular depth up to which the light penetrates, this is something called as absorption depth. Absorption depth. And this particular alpha gives the absorption coefficient, but if you want to find the absorption depth, that is equivalent to 1 over alpha. Okay, this is something called as absorption depth, or it's called as penetration depth of the light, which is equal to 1 by absorption coefficient. Because the unit of absorption coefficient is 1 by meter, so unit of this will be meter. So it gives you the penetration of the light inside the medium. Okay, now where does it come from? It comes basically from a simple law. This is which is basically called as Beer-Lambert's law, and it comes from a solution of a simple differential equation. You might have heard about Beer-Lambert's law. It says that if you have a sample like this, if you have intensity I coming out, I falling onto this particular sample, then the output intensity will be basically equivalent to initial intensity e to the power minus alpha times x. Okay, so this is the actual law. If this is the x dimension, this is the actual Beer-Lambert's law. Beer-Lambert's law. But where does it come from? It comes from the fact that the change in the number of photons with the depth varies as the initial number of the photons. That means if you have a differential equation like this, where the photons, the change in the photons with respect to x is proportional to itself. Whenever you have a differential equation where a quantity is proportional to itself, that means if this particular thing increases, this is going to reduce. Always the solution is going to be exponential. That means dn by dx is equal to minus alpha times, let's say, n, minus alpha times n, and you can solve it as dn by n equals to minus alpha times dx. You integrate both sides, you're going to get it as maybe n equals to n naught e to the power minus alpha times x. Okay, this is going to be the this is going to be the photon concentration inside the medium. Okay, so similarly you can write intensity, similarly in this fashion you can write the intensity with respect to x is proportional to some minus times I naught, and it's going to give you the intensity equals to I naught e to the power minus alpha times x. This is not I naught, this is I. Okay, so this is the exact form of I should say Beer-Lambert's law, and it's applicable in all of the systems. Even in radioactivity, you might have studied about the particles decaying. Whenever you have a decaying system, that number of particles decaying is proportional to the to the number of particles itself. The solution is always going to be exponential. Okay, it's going to be exponential decay. It's going to be either exponential decay, or it's going to be either a rising exponential. It depends upon what system we are studying. That's the general form of the differential equation. Okay, so what this intensity is now, this particular thing is the transmitted intensity. It determines the how much light is transmitted. So the transmitted intensity is initial intensity e to the power minus alpha times x. So that's why you see, if let's say at x tending to infinity, the transmitted intensity, what will be it? It will be e to the power minus infinity, that will be 0. That means if you make this particular medium infinite, then if you have a light coming through this, you won't get any light out from it. Transmitted light will be 0. And if you go on reducing this particular dimension, if you go on reducing this, let's say up to this, initially it was like this, and this is x. Now you have certain probability that you have certain transmitted light, because you have reduced the x. So lowering the X also has the impact on this particular light going out from the medium. And what is this X? This X is the dimension through which the light is going into the medium, going into the material. Okay, now it also depends upon this absorption coefficient. This is really important. And what this absorption coefficient depends upon? This is absorption coefficient. It depends upon the medium itself. And what determines the absorption coefficient is basically the band gap. Okay, it is basically the band gap which allows the photons to get absorbed or transmitted or reflected or any other scenario. Because overall, whenever something is hitting, if a beam is hitting a medium, either it can get reflected or it can get absorbed or it can get transmitted. These are the three scenarios which can happen. So if it gets reflected, let's say this is R, this is incident beam I, this is reflected beam R, this is transmitted beam T, and there is some part is absorbed. So overall you can write that absorption plus transmission plus reflection is equivalent to 1. This is the general form. Okay. Whenever a beam or whenever any form of light hits any medium, it's not only semiconductor, it's any medium. It's maybe a table, plastic box, anything. So some part of it gets reflected. If something is getting reflected from it, that's how you are able to visualize or view that object. If this part is not there, then you won't be able to see the object at all. That is the reflected light you are seeing from any of the object you are observing right now. And if it is transmitting, that means the material is, let's say, transparent to that wavelength. If let's say you have a glass pan here and you are the visible photons are hitting it, the visible photons are hitting it at wavelength from 400 to 700 nanometers, the photons are easily going through this. Why? Because if you have this is silicon dioxide mostly, which is the glass pan, which is your glass window, it has a band gap of over approximately 9 electron volts. Okay, so what happens is that this light is going straight through this material. It's not even interacting with I should say, the electrons and the charges present inside the system. There are different kinds of interactions, but what is happening to this light is going straight through without any interaction because the energy of this visible light is not enough to cause any transitions in the silicon dioxide. So it's going through. Now, on the other hand, if you have a, let's say, a lower band gap system where you have energy band gap equals to maybe 1 electron volt, it may so happen that if a light comes in the visible region, some electrons will get excited here. That means some part of the light will get absorbed. Okay, some part of the light will get absorbed. Okay, and again, all of the energy will not get absorbed. Some part will get transmitted. Okay, this is the transmitted part now. So this will be the absorbed part. This will be the transmitted part. And reflection is a different scenario. Definitely, there has to be some reflection. If there is no reflection, then you won't be able to see the material itself. Reflection is always there. So there is some reflected part. And why is there a reflection in the medium? It is because of the electrons oscillation in oscillatory behavior in electric field. In electric field of what? Electromagnetic wave. I don't want to go into that detail. Basically, if you have a reflection versus the frequency of a wave of the incoming wave, which is the light, then you have a curve something like this, where this particular frequency is called as plasma frequency. If the frequency of a light is less than the plasma frequency, you have the reflection. If it is greater than plasma frequency, you won't get any reflection at all. This is the actual rule. And most of the things which we see in the visible range are below this particular plasma frequency. So let's not go into that particular depth. But what my point is that reflection comes from every object which you see in this particular universe. That's how you are able to observe the objects around you. Okay, and certain materials which are transparent, like the silicon dioxide, you have the complete transmission, as well as there is some. Now you will see that you're getting some part reflected also from the glass pan. That's how you observe the glass pan basically. But you notice that if you have a very clear glass pan, clear glass window panel, it looks like as if there is nothing there, because if you have a crystal clear glass, nothing in it interacts with the light, then light goes through it straight. It does not interact with anything, and you are not able to differentiate whether there's a glass there or not. But it happens only if you have a very crystal clear quality glass. Okay, otherwise there will be definitely some reflections. And a very little part of it gets absorbed, but most of it, I should say 99.9% of the light gets transmitted through the glass pan. Now, this is the exact story of all of the semiconducting devices. Okay, let's say if you talk about maybe silicon, if you talk about the silicon, if you talk about the gallium arsenide, these are the materials which are used to make something called as solar cells. These are used to make solar cells, photodetectors, as well as the photodiodes. Okay, and the band gap of this is approximately a 1.1 electron volt, and this is approximately maybe 2 electron volt. Just cross check the values. And it so happens that the light in certain region can cause transitions in the silicon, it can cause transitions in the gallium arsenide. But if you have, let's say, something called as gallium nitride, okay, it's another material, its band gap is approximately 3 electron volt, then you will see that it is absolutely transparent at visible wavelength. At visible light, it is absolutely transparent because visible light's energy is not enough to cause any transitions in the gallium nitride. Okay, 3 electron volt is a huge value. Visible light does not have an energy of the order of 3 electron volt. If you have 400, visible light is between 400 nanometers to 700 nanometers. So you can convert this into energy by using Hc over lambda. So you will get the value of the energy ranges for the visible transition. Okay, so this will be the higher energy photon. This will be the lower energy photon. Okay, so that is what is necessary. Now what causes basically these particular what causes basically these transitions, and why do certain materials have better transmission or reflection or absorption quality than that of the others? Now, what does it depend on? It depends on two things: whether a material is a direct band gap semiconductor, or whether it's an indirect band gap semiconductor. It's a very crude, I should say, differentiation between the two materials. In actual sense, you will see that you can always convert a direct band gap into an indirect band gap and indirect to a direct band gap. Let's study about what first these two things are. So in the indirect band gap, you have, if you talk about the E versus K diagram, if you have something like this is the minimum of this is the conduction band, and if you have another parabola which is the maximum of which is the valence band, and this is E, this is K. If you have the minimum of the conduction band and the maximum of the valence band at same K value, then this is called as direct band gap semiconductor. And what happens when it's at same K? Well, K determines the momentum of the electron. It's the momentum of electron. That means whenever let's say a light is coming from this end, H nu, it is creating electron hole pairs, hole here, electron here. This electron goes here. You see, when the electron makes transition to the conduction band, it does not change its momentum. So the K value stays same. Okay. That means whatever was the K before, the momentum before, it is the same momentum. It's at the same K value. And to be exact, at this particular point, which is something called as gamma point, it's called as gamma point. Oh God. So this is called as gamma point. At this particular point, you have K value to be equivalent to 0. Okay. So what is now the significance of these particular of this particular direct band gap semiconductor? Now you see that there will be, whenever the light is going to come, it's going to create the electron hole pair. It does not need to change the momentum of the electron in order to make any transition. Okay, so that is the advantage. Whenever the H nu, if this is gap is something like something called as energy gap, whenever the H nu is greater or equivalent to energy gap value, it can create electron hole pairs easily. Okay, why? Because now you see that the electron can now just increase in the energy value. It does not have to change its momentum. Okay, so it just changes the just electron just changes E value without changing without changing K value, without K changing. And it becomes easy for the electron to have this particular transition. And if you want to study deeper, there is something called as selection rules. Selection rules. This is a topic of something called as quantum mechanics, why these effects happen. We won't go into that detail, but if anyone is interested, they can just look for something called as selection rules. Basically, there are a certain set of rules in quantum mechanics which governs the transition of the electron from lower state to the higher state. But those are just these rules where the I should say the transition happens without the change of the momentum. Okay. Now, this is the direct band gap semiconductor. We will talk more about it just in briefly. But what is indirect band gap semiconductor? Now, if you have a scenario, if you have a, let's say, a band like this, you can have any sort of bands. And you remember, just keep this in mind. This is the first Brillouin zone. This is the first Brillouin zone. This is the gamma point here, which I told you. And at this particular point, it may be some point called as X point. This may be some L point, and these are different directions in the lattice. Just remember this. And we have talked it before. So let's say if this is the first Brillouin zone, let's say this is the first Brillouin zone, and this is the let's draw it here. This is the minimum of this. This is the valence band, and this is the minimum of this. This is the minimum of the other band. Let's say this was the first Brillouin zone. First Brillouin zone. But what you saw is that whenever the photon will come in this particular scenario, it won't be able to create the electron hole pairs, because for the electron to reach the minimum of the conduction band at this particular position, the energy gap value is very high. So let's say call this an Eg dash. So H nu will be, if H nu is much greater than Eg dash, then it can create transitions. But it so happens that this particular Eg dash value is huge. It's of the order of maybe 8 to 9 electron volts, or maybe 4 electron volts. If it is greater than the incoming photon energy, then photon won't be able to make the transitions. Okay, as simple as that. Now, what is the other possible scenario for the photon to do? Other possible scenario is, let's say if there is a photon incoming, the electron hole pairs can get generated like this. You can have a hole here, you can have an electron here. And how does this happen? This happens via other processes. That's why I talked about, when I talked about the direct band gap semiconductor, you have to draw it at the same K value. If you have an electron here, so if a photon comes, it knocks the electron to this state. Well, why does it exactly go up in energy? If the photon is coming in this direction, the electron, theoretically, what our mind tells us, the electron should go in this direction. Why is it going straight up? Okay, why isn't it going in this particular direction? It is because this particular photon, it has a very small momentum. Okay, it has very small momentum, and that momentum is not able to change the electron momentum at all. It's not going to change the momentum of electron. Wherever the electron was, it's going to just go higher in energy without any change in the momentum. All right. So now what makes this particular transition possible? Well, it turns out, let's say if there are certain other scenarios in the certain other I should say processes happening in the system processes. It may so happen that electron goes here. Maybe there is a certain state present here, and another set of energy comes at this particular another set of perturbation comes at this particular level and makes the electron to go at this particular state. And this can be maybe this can be another photon, and this can be even a phonon. Okay, a phonon is because of lattice vibrations. Lattice vibrations. We've talked about it in detail in the previous classes. So, so these particular particles, which are other quasi-particles, these are called as quasi-particles. The phonon is called as quasi-particle because it's not a true particle, it's just a field. So they make the electron transition possible. And, and why do they make it possible? Because they have the momentum much greater than the photon because of huge energy space they occupy. Okay, so the phonon momentum, if you talk about the phonon momentum, which is h bar times omega, where this is the omega, which is this is the frequency of the phonons. Okay, so it has the ability to change the momentum of the electron. Okay, but the photon momentum is so small, at least up to what we call as linear regime, where the intensity of the light is not much greater than certain threshold value. If the light is not that much intense, it cannot change the momentum of the electron. But if it is much greater than some threshold value, you might study in higher classes, maybe that is a research topic. Basically, it can definitely change the momentum of the electron. But to our knowledge, to right now, we are assuming that light is not able to change the momentum of the electron at all. What it does is that it can bring it above in higher in energy, and certain other processes can mediate this particular transition from this level to this particular level. And you see that, let's say the k value was here k1 and the k value was here k2, then you have the momentum change from k1 to k2. Okay, and overall momentum has to be conserved. So if this momentum value, let's say at this particular energy, you have a phonon which came in this direction. Let's say it has momentum, let's call it q, and the electron here initially was having momentum k1, and final momentum is in this direction. So this is the final momentum direction. So it's like these are like vectors, because momentum is a vector. So if this is the initial momentum of the electron, so electron was initially going like this, then it went here, there came a phonon h bar omega q, it went in this direction, it went here, and this is the overall direction, and this is the overall momentum. This is the overall momentum. Let's say this is the let me call this as the momentum of the phonon as q. Let me call this as k. uh, Let me call this as k. And you see that overall momentum is it has to be conserved. The momentum of the electron plus the momentum of the phonon, they have to be totally conserved, and all have to finally add up to zero. Okay, and what is going to now happen? Basically, this is the I should say the basics of something called as Feynman diagram. So that is where the higher regime starts. But we won't be definitely going into this particular picture. But if it is the same picture. If you have an electron, you have some quasi particle coming in this direction. The electron maybe will go in this particular direction, and you will be having the overall wave vector which is in this direction. Let's call it k dash. This is the electron momentum, and you can see that overall momentum will be something k minus q. And that is the essence of how you deal with particles. And this is the core fundamental particle physics aspect here. But we don't want to deal with this particular thing. We just want to understand how the electronic transitions are made possible. Now, this is the scenario for the direct and indirect transition. Now, it so happens that most of the material around us which we have used till now are something called as indirect band gap semiconductors. And why is it the case? let's say you have a let's say you have silicon. In silicon, it is used till now in the solar cells, but it turns out it's a very, I should say, a bad material. It is used, but it is very bad material till now, because up to now the maximum efficiency of this silicon solar cell has been approximately reached up to maybe 27 to 30%. This is the maximum efficiency of the solar cell. A maximum efficiency means output power divided by input power. Okay, what is output power? Output power is current. What is input power? Input power is light. So it is the current, or I should say current times the voltage divided by the power you give it in the form of the light. So that is the efficiency. That means the ability to convert electron hole pairs into the current flowing in the circuit. And for silicon solar cell, it's very, I should say, very low even till date. That's why it's a very hot research topic. The solar cells is always a hot research topic because we want to increase this conversion efficiency. The reason is because it's an indirect bandgap semiconductor. Because the electron has to go from this region to this region. Maybe let's say it can go up to this certain mid gap region, or where if there is some defective state, it can even, then other processes has to happen, which are the phonons. They can just bring this electron to this particular state, and you have an electron hole pair generated. And whenever the electron hole pair is generated, they get splitted, I should say. They can recombine, as well as they can get splitted by the internal electric field present inside the p-n junction, so that these electron hole pairs can be recollected. Okay, that is the fundamental of the solar cell. But what limits the performance is this particular process. This particular process limits the fundamental efficiency of the solar cell, because you are you are totally, I should say, first of all, wasting energy in this particular process, as well as you are depending upon other processes inside the system to happen. So whenever you talk about the phonons. The phonons are the vibrations of the lattice. Vibrations of the lattice. Okay. So if it is mediating, if it is helping in the electron hole pair generation, apart from the light, then you know that this phonon energy depends upon the temperature. And you know, whenever you place a solar cell in a ambient atmosphere, in a external atmosphere, ambient environment, the temperature keeps on changing. So T keeps on changing. And what it does is that it creates, I should say, variation in the charges as well as the currents flowing in the solar cell. So that is why it is the fundamental, I should say, the variation inside the device solar cell particularly happening because of the temperature change, that also controls how efficient the solar cell is. That's why you mostly see that these particular solar cells degrade even if it is very high temperature, or if it's very low temperature. They because this particular thing is mediated by the phonons, and phonons are the lattice vibrations, and the lattice vibrations depend upon temperature. If you go to 0 Kelvin, if you reduce the temperature to, let's say, 0 Kelvin, you will see very few lattice vibrations. Even lattice vibrations totally cease to exist, and you won't see these particular transitions to happen at all. So it says that the ambient atmosphere or ambient environment has a very significant effect on these particular devices, because they are dependent upon such processes which are mediated by the temperature. Okay, this is about it. Now what we are going to see is that what we are going to see, just let me check. Now you have a whole band of wavelengths of the light. What the light source you have is basically the sun, and it has a spectral range. It does not give only a single wavelength. It has a spectral range of wavelengths, because sun is something called as black body. Black body is which emits a whole range of radiation and the wavelength. Okay, it's like a, it's not an ideal black body, but what happens is that when you draw the spectral curve of the radiation coming from the sun, let's say sun is emitting certain radiation, if you measure its response in the frequency or the wavelength, you get a curve something like this. Okay, this is called as black body curve. This is called as black body curve. and it is very, I should say, it was predicted by Planck. That's the actually the basics of the this curve was the start of the quantum mechanics. But if somebody's interested, maybe you might look. This curve is the start because it it started the quantum mechanics in a way that people were not able to explain why this particular curve is, I should say, why the particular spectral range is occurring in the nature itself. Initially, what Planck did is Planck was able to explain. Basically, there are two parts in this curve. So there is this part exponentially, and there is this part exponential decaying part. So people were able to basically map this decaying part. They thought, yes, that this particular decaying part it can be mapped, but they were not able to explain the blue part, which is the rising part. And if it is, this is the this particular thing is irradiance. Irradiance. We will talk about what irradiance is. It's basically watt per meter square per let's say per micrometer, and this is the wavelength in micrometers. So, so this is the power of light irradiating on a surface per micrometer. It's like if you have a micrometer of size, and the power irradiating on it is basically the irradiance. So it's the power per unit length dimension of that particular or per unit dimension of that particular system. So that is what is the irradiance, because power is basically energy per unit time. So you can write it as watt per meter square. Okay. So now initially what people thought is that they were able to explain the red curve. There was something called a Rayleigh-Jeans law. Maybe you might have heard about Rayleigh scientists, Rayleigh scattering and other things. Rayleigh's law. But they were not able to explain the blue curve. How does the initial rise happens in the blue curve? And this is something called as ultraviolet catastrophe. In the then this is the beginning of quantum mechanics. Basically, Planck was not able to explain why the ultraviolet catastrophe happens, because if you go down lower in the wavelength, you go to the ultraviolet range. You go higher in the wavelength, you go to the IR range. Okay, so this is, I think this wavelength is around maybe somewhere, this may be 250, not 250 microns. It is approximately zero point 0.2 micron, and then this is the maybe around zero point 0.3 to zero point 0.4 microns, which comes out approximately in the ultraviolet regime. So that was basically the prediction of the Planck that uh, that this ultraviolet catastrophe, that there is a sudden shoot up in the irradiance in the black body spectrum at the lower ultraviolet wavelengths. And what Planck suggested is that later on he said that the light is not coming in the form of a continuous wave packets. It's basically coming in the form of a something as a quanta of light, which is the packets. And that created a problem in the whole scientific community, because it gave the idea of that nothing is continuous in nature. It's a discretized packets which is coming. And how this basically relates with it, it's a very deep theory, scientific theory. In order to understand it totally, you have to understand the basics of it. So it's just a brief overview of it. Then this particular problem sorted out the something called as this ultraviolet catastrophe, and people were able to now clearly give this particular prediction that yes, this is going to happen at a particular lower wavelengths or ultraviolet regions. Okay, so what now happens is that this particular curve is the curve coming from the, it's the spectral irradiance of the sun. Okay, so it's the spectral irradiance of the sun. So why is it necessary for us? Because using it, we can basically predict which part of the spectrum will get maximally absorbed in the solar cell, because we want that absorption to happen, right? We don't want the light to get transmitted through the solar cell, because then it will be transparent, and we want it to get absorbed to create electron hole pairs. Okay, if you have a, let's say, a solar cell, if you have a solar cell, which is basically a PN junction, it's basically a PN junction. All right. So if you have a solar cell like this, where you have a flat Fermi level, flat, which is this is the p side, this is the n side. Later on, we will see the p side is made smaller than that of the n side. Why that is the case, we will talk about it. This is the depletion region. You want the electron and hole pairs to get created. Okay, when will they be created? They will be created when the light coming is absorbed by them. They will absorb the light, light's energy will be absorbed, and there will be transition. And later on, these electron and hole pairs will be separated, and they will give rise to a current in the circuit. This is this direction, and this will be the direction of the current, light current flowing through the circuit. So now you see that this particular, the light coming in, how much it's absorbed, it depends upon the absorption coefficient. We saw, but we saw earlier, but this absorption coefficient depends upon the band gap. Okay, and if it depends upon the band gap, then what ensures that the absorption takes place is the light energy, which is h nu. Now, if this h nu is greater or equivalent to the band gap, then it's going to create the electron hole pairs. Okay, that is the fundamental thing. And now it boils down to this particular curve where the maximum spectral irradiance is present in the sun's spectrum with respect to the wavelength. Okay, now let's say you have maybe you have something called something like silicon. If you have oh god, if you have a silicon with a band gap of approximately 1.12 electron volt, then if you have, let's say, there is this is basically this is basically irradiance. If you want to count the number of photons, which is the photon flux, which is the photon flux, which is the number of photons irradiating on per unit area per unit time. So this is the flux. That means it's the number per unit area, let's say meter square per second. If you want to count this photon flux, how you can count is basically, let's say if you want to count it at this particular wavelength, let's say this is 0.5 micrometer. How, what you can do is that you can count flux photon flux of what, which is coming from the basically the sun external source. It's not only applicable to sun, first of all, it's applicable to any external light source, whether you are giving the light with LED or a torch or a candle or laser. It's applicable to all the photon flux concept as well as every other concept which we will be discussing today. We're just talking about the sun because we are here talking about the most particularly talking about the solar cell, and the source of I should say input to the solar cell is definitely the sunlight energy in the form of the electromagnetic waves or the energy of the sunlight. So if you want to compute the photon flux, how you can basically compute it is using the wavelength of the input light and dividing it by the energy of the band gap energy basically. And if you want to convert it into, let's say, let's call it, if you are, oh god, why is it, let's say if you have energy of, you want to, you first of all you want to know what is the energy of this 500 nanometer, or let's keep it a micrometer. You want to know what's the energy of this particular photon. The energy of this particular photon will be basically hc over lambda. Okay, so now what will be the photon flux? If you are given, let's say, you should be first of all knowing the spectral irradiance at this particular wavelength. Let's say this spectral irradiance is maybe 10 to the power 3 watt per meter square per micrometer. Then you can compute the photon flux as spectral irradiance times the wavelength of that particular light divided by the band gap of the that particular I should say system, and into the 1 over electronic charge. This is going to give you the overall photon flux which will be irradiated on this particular medium. And I think I did some mistake here. Maybe let me check. Hmm. Okay, actually the flux, the spectral irradiance is basically the flux times the energy of that particular photon. This is the photon energy divided by the wavelength. So if you want to compute the photon flux, it will be spectral irradiance times the wavelength divided by energy of the photon into the electronic charge to convert it into electron volts. And okay, so I did a mistake here, yes, that's what I was seeing. This is basically the energy of this particular photon or the energy gap. So this will be the photon flux. Why would energy gap come into this particular flux, photon flux concept? Okay, yeah, that makes sense. Because in order to compute the number of photons coming from a source, why do you need the energy gap? You just need the particular inputs of the light source, and the inputs will be the wavelength of the light, energy of the light, and spectral irradiance. That will give you the flux. And let's check the units. Watt per meter square per micrometer, and yes, this is fine. Into micrometer divided by let's say joules. This goes. Watt can be written as joule per meter, joule per second. 1 by joule. This goes. This is 1 meter square second. Yes, this is exactly the flux. That is number per unit area per second. Okay, so if you want to compute the photon flux, which is the number of photons coming to irradiated on a particular area per unit area per unit time, is basically spectral irradiance times the wavelength of the photon divided by energy of the photon. Okay, and you can multiply it with electronic charge in order to convert the units. All right. So now why is that necessary? Because that is going to tell you how many number of photons are irradiated onto a particular surface. Let's say if you have a PN junction, and let's say if you know this particular surface, how much surface is getting irradiated by the sunlight, then you can basically you can knowing the photon count, basically knowing the photon flux, you can design your solar cell accordingly in order to have the maximum photon flux onto this particular surface, because it depends upon this particular area on which it is getting irradiated. And because this irradiance is basically the watt per meter square, so the area comes into irradiance itself. Area information is itself embedded in the irradiance, this particular thing. Okay, this is the area information. And if you have a, let me just tell you briefly, you might get confused about. If you have a beam of light, if this is a beam of light, this is a beam of light. So this has some beam width. Let's call it, D, and let's call this radius as R. And if it is moving in this direction, then it has intensity which is equivalent to energy per unit area. Correct. And what will be the area? It will be the area of the circle, okay, which is pi r square, okay, or that you can also write it in terms of the diameter, but you can write it as E over pi r square. So this will be the intensity of this particular beam of light. So this is the beam of light moving in this direction. Now if you want to compute the power, you can write power equals to energy per unit time, or you can write energy in terms of the intensity times the area, and you can write power as an intensity area over time. So if you know this particular thing, you can compute the power of this particular light beam. So this is typically applicable whenever you have a light source with certain defined I should say beam width. So that's why if you see when this intensity has a unit of watt per meter square. Okay, not watt, sorry, it's joules, joule per meter square. Okay, and then if you go to the intensity divided by time, it gets converted to joule per meter square per second, and it will be watt per meter square, because joule per second is watt per meter square. So basically the intensity and the area information, what I'm trying to convey here is this area information of the light getting irradiated on the medium. It is embedded in the intensity itself, which is in the denominator. So it is embedded in the spectral irradiance itself. Okay. So if you somehow, that is why if you, that's why you, if you have a sun, if you have a sunlight, and if you concentrate the sunlight using a lens, if you concentrate, if you, these are sunlight, if you concentrate using a lens at a particular area, what you are reducing is this particular beam width. You are reducing this beam width. Okay, you see this. So what you are increasing is the spectral. You are basically increasing the intensity at this particular position because you are decreasing the area. Okay, decreasing the area increases the intensity, and it will definitely is going to increase the power of this particular light source. And that's why you see whenever you increase the intensity, whenever you focus using the lens, it burns the material even from the sun. Otherwise, sun's energy is spreaded like this. But if you focus it, you are focusing it and you are increasing the intensity so much that it creates the catastrophic damage inside the material. Okay, that is the fundamental concept where the what the area of the beam, what of the area of the beam, and where does it come into picture. Even certain, I should say, there are certain techniques which basically focus the sunlight onto the particular solar cells in order to increase the efficient, in order to increase the number of, I should say, photons in that particular, not the photons, in order to concentrate those particular photons onto a particular region. Okay, that has been shown by some people to increase the efficiency, but it's quite a, I should say, a research topic which is under progress right now. So now where we are going heading now, what we are doing now, what we are doing is that we are heading, we are going to the topic of PN junction being irradiated onto the light. Okay, let's say you have a PN junction. Let me check whether this is covered. Okay. Mm, yeah. So you have, let's say, maybe I have shown here. Yeah. Okay. Uh, So you have a, let's say you have a PN junction like this, and you have a light irradiated onto the material where the light wavelength is much greater than the band gap. So whatever the light is coming here, it's giving rise to the electron hole pairs. This is hole, electron is here. Because the energy is much greater than energy band gap, this much energy of the electron will be the kinetic energy. What I told you in the last class. If the electron is here, it has only potential energy. But if the electron is above the band gap, above the minimum of the conduction band, then it has kinetic energy as well. Okay. Then how its transition will take place? It will drop like this. Okay, that is how its transition will take place. And the kinetic energy it will lose, it will get converted into potential energy. Total energy has to be constant. So whatever the kinetic energy it loses, it gives it to the system in the form of phonons. Okay. And when it reaches the minimum of this band, electron can go and recombine with the hole, then it can give off the photon again. Okay, that is the exact scenario what happens. The electron's excess kinetic energy gets converted into other quasi-particles, which are the phonons, and these phonons heat up the lattice. They heat up the lattice. Well, not on all phonons are bad, but some phonons. They heat up the lattice, but I don't want to talk about what phonons are good and bad. But they give up rise to the lattice heating. When it reaches this particular point, minimum of the conduction band, then it recombines with the holes, and you get a light out because of the selection rule. Because now the energy is exactly equivalent to the band gap energy, and that energy is giving rise to a photon. Okay, so this is the fundamental picture of it. Okay, so now it turns out that electron it's getting converted into different quasi-particles when it's making the transitions. It's getting converted into phonons and photons, and it's quite a, I should say, a particle physics, mostly a particle physics based topic where people are going mad or crazy in this particular area. What is happening? But let's talk about this particular thing. Whenever light gets irradiated onto this, and light is getting irradiated throughout the system. But our major concern is this particular depletion region, because you know that inbuilt electric field is going to separate the electron hole pairs. Whenever the electron hole pairs will be here, this will go in this direction, this will go in this direction, you will be having the external current flowing in the circuit. Well, now, first of all, we are here talking about something called as photodetector. Okay. In this particular scenario, you apply a reverse bias in this section. You reverse bias the system. Okay. And whenever you have the reverse bias, you know how the description of the but the band diagram looks like. Let me you know how the description looks like. It looks like something like this. You have a very huge difference between the Fermi quasi-Fermi level on N side and quasi-Fermi level on the P side, and you have a huge barrier here. And this huge barrier actually ensures that if somehow electron hole pairs are generated here, they will rush down the slope. This will go here. And because of it, there will be current flow. Now, why do we apply the reverse bias? Why don't we forward biases? Because in the forward bias, you will have the current flow. As simple as that. If you have a PN junction and if you forward bias it, it will already give rise to current in this fashion. This is the current, this is the voltage. This is the voltage. And if you have the current, which is exponentially rising current, so it's a huge current after some voltage, which is the cut-in voltage. You don't want that current. You don't want yourself to make the device conducting. So that's why what you do, you make it reverse biased. You remove this, you reverse bias it. Now you assume that in the reverse bias no current is flowing. But when the external perturbation comes in, which is the light, it generates the electron hole pairs. And what it does, it increases the overall current in this particular system. And you will see that this rises to this particular level, it will go on increasing. That means this I naught increases, the reverse saturation current, which is the I naught in the diode equation. Okay, so overall now you have the equation of the overall current will be now the current because of the light will be flowing in this direction. Okay, and you will see that the total current will be given by the this particular thing plus the diode current equation. And you know that it can be written as total current will be light current plus the overall saturation current e to the power qv by kt minus 1. So this is the total current equation of the solar cell. And this light current is flowing because electrons are going in this direction, holes are going in this direction, and electron and the current will be overall in this direction because of the light current. So it's opposite to that of the what was initially assumed to flow. Because initially you remember when the diode was under when the diode was under forward bias, so the electron goes in this direction in the forward bias and hole goes in this direction. So that overall current flows in this direction. So that's why the current direction is like this. But in this direction, you have the opposite flow of the electrons and the holes. Okay. So now what does this give rise to? This gives rise to a peculiar phenomena, what is called as the photon detection. And and that is why you see that whenever you draw the curves of the particular photodetector, you see these curves increasing with increase in the illumination. If you illuminate more light, you are basically generating more electron hole pairs. So the generation is increasing. So you see that more electron hole pairs are getting generated. You have the increase in the reverse saturation current with the increase in the light illumination falling onto this particular system. And what does it basically depend on? Well, it depends upon certain factors. Those what are those factors? Those factors are how much is this particular thing wide, how much this is what is the width of this particular thing, what will be the width of the depletion region formed. Usually what we want is that we want this depletion width to be larger. Okay, and that's why most of the times when we make it, we want this particular thing to be larger so that electrons hole pair can get separated easily. And uh, and they can only get separated if we make this larger, and if you have a p and n side, so that whenever the electron goes into this direction, hole goes into this direction, you know that whenever the hole will come here, there will be some recombination also. Okay, so you want to ensure that at least this length is much greater than the diffusion length of the holes. So let's call it P, let's call it PL, let's call it LP, let's call it LN. You want these particular lengths to be much greater than diffusion lengths because these electron and hole pairs should recombine externally. They should not recombine in the circuit. They should not recombine in the material itself. Okay, so that for us we can detect it whenever the light will come. They will generate the electron hole pairs, and you can detect them externally in the circuit. Okay, so now what is the overall scenario? So let's say this was for the maybe this is for the photodiode. Yeah, this is for the photodiode definitely. Total y minus L in the expression. You're talking about this particular thing. Okay, I might have maybe mistakenly here. Okay, yes, 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 yes. Basically, this is the equation. If you This is the scenario if you have a P and N, and if you have a external thing, if there is no external battery source present, then if you have illuminated with some light, there will be the light current generated, and you will be having the total current equation like this. This is not the equation for the solar cell, pardon me. This is not the equation for the, I should say, this is not the equation for this particular scenario, what I have shown here. It's not the equation for the photodetector as such. Okay, so the light current overall will be the scenario in case of the solar cell. Maybe I might have mixed it up. Let me just clarify further. So whenever you have a system, let's say like this, you can have the generation of the light current in this direction if there is a light illumination, and you will have some output load along which you can always measure the voltage, and then you can have the this is basically the functioning of the solar cell whenever the light gets irradiated onto this particular system. Now this particular thing I mixed up. This was for the photo detector. That's what I actually showed up. This was for the photo detector. Let me draw it. This curve is basically for the photo detector, not for the solar cell, because this is in the third quadrant. And you know that whenever you have a particular system of curves, if if this is the diode equation, this is the diode curve, this is the first quadrant, second quadrant, third quadrant, and fourth quadrant. So what happens is basically this is for the normal PN diode. And if you have the reverse equation, the reverse bias current, and if it goes on increasing with the photon illumination, okay, then this is the for the photodiode, which or the photodetector, okay, and this increases with increase in the illumination of the light, okay, and here you see that overall the voltage is negative, the current is negative in the negative direction, negative axis. So overall the product of the voltage into current will be positive, and it means the power is absorbed by it, the circuit. And for the solar cell, you see that this particular curve basically goes like this and makes a transition into this region like this. Whenever you have a solar cell, you have a curve something like this. It goes into the fourth quadrant. And because of that, you have two regions. One region is here, one region is here. You can basically call these some voltage. This is some value of current, and you see that here the voltage value is positive, the current value is negative. So the overall P is equivalent to V times I will be negative. So that means the power, overall the power is being given out from the system. So the power, it is generated power. So there is a different definition in the circuit terminology for positive and negative power. So, but that is how we define it in terms of the devices basically. But don't get confused if you read something different in a network analysis classes or maybe some other circuits. Okay, so what happens is that if you have this particular solar cell characteristics, you get you get these particular characteristics, and you want to know what will be the ideal scenario for a solar cell will be to get a curve like this. But this will not happen. But this is the ideal scenario of the solar cell curve, where these particular points, this is called as open circuit voltage, and and this is called as short circuit current, these particular values. And the area of this particular square, it is necessary for this area to get maximized. But when you draw the realistic curve, this black curve is basically the ideal. When you see the ideal solar cell curve, you have something like this. So this is the real. So you want to match this real curve more and more to the ideal curve, so that you can have the VOC and IOC product maximum. And that's what you will be seeing in the solar cells. You want to maximize this particular area, but how you're going to do is that, I should say, if you want to maximize this particular, you want to not maximize, you want to basically minimize this particular area, so that you can have, let's say, if this point is here, this point is here, this is the area of this particular square now for the real conditions. Then this point, let's say if you call this point as Vm, you call this point as Im, then you define something called as fill factor, which is basically the ratio of the power in both the scenarios. Okay, so this fill factor, you want to ensure that it is approximately equivalent to 1. So when that will be equivalent to 1, when it will be 1 when Vm Im is equivalent to Isc Voc, and when those both quantities are equal. So ideally you want this to be a square form in order to increase this particular fill factor, which determines basically the efficiency of a solar cell. Now you will see that this particular determines the efficiency of a solar cell. Oh God, efficiency means efficiency of a solar cell. So it determines how many photons will get converted into electrons. Okay, and that basically controls the efficiency of the solar cell. Now, how is that controlled? That's what we are going to see. Let's say you have efficiency. How do you define efficiency? Is something like power out divided by input power. If you have a black box, which is a solar cell, you are giving some input power and you are getting some output power. What is this input power? This is light. What is the output power? This is current, or voltage, or electricity, or the electric power. So the P out is basically what you are getting out from the solar cell. Okay, and P in is basically the power of the light source, which is being irradiated onto this particular solar cell. And now you can write this Vm Im using this particular equation. You can write Vm Im to be equivalent to Voc Isc into fill factor divided by the input power of the solar cell. So now you see that the efficiency of the solar cell directly depends upon this fill factor. So now what do you want to do? You want to increase this particular fill factor as much as possible. And for it, you want to increase this particular thing. If you want to increase this particular thing, that means you have to increase the orange square in order to ensure that it matches the black square, the bigger one, so that you can make it bigger and bigger and the area under the curve increases. So that is the exact scenario we want to do in order to increase the efficiency of a solar cell. But there is a trade-off. Trade-off means if you increase one thing, other things are affected. Let's say if you want to increase the efficiency of a solar cell, you will see that you can increase the short circuit current. Okay, but for increasing the short circuit current, you can reduce the band gap of the solar cell, because what does this depend upon? This depends upon this depends upon I naught, which is basically the short circuit current flowing in the circuit, and that basically depends upon the band gap, because this depends upon intrinsic concentration. Intrinsic concentration depends upon band gap. Okay, so ISC can be increased if you decrease the band gap. And efficiency can be increased also if you increase the VOC. But for increasing the VOC, you have to reduce the band gap. Okay, but that means that there is a trade-off. If you decrease the band gap, you increase the ISC. If you decrease the band gap, you increase the VOC. Maybe I might have mentioned it here. No, I mentioned this is ulta. So if you want to increase the VOC, you have to increase the energy gap. So that means these two are opposite of each other. In order to increase the product ISC times VOC, you want both of them to increase. Okay, but if band gap is increasing, ISC is reducing and VOC is increasing, and it's not going to do any good for us. So that's why always a trade-off whenever the people design the solar cell, they design it in such a way that this particular trade-off is, I should say, the solar cell efficiency is not limited by this particular trade-off. Okay, so there has to be some optimum energy gap value, which basically gives you the best ISC times VOC product, so that the efficiency is overall increased. Okay, so that means if you have energy gap a material in which the energy gap is more or high, then it can increase the short circuit current, but it will give you the lower VOC. But if you have a, let's say, a material with band gap, maybe this is low, not high. If this is low, but if you have a material with high band gap, then what is going to do it's going to increase the VOC, but it's going to reduce the short circuit current, and overall the efficiency is going to be determined by that. So that is the fundamental limit of the solar cell basically right now, in order to increase the overall efficiency of the solar cell. And one more important point to note here is that whenever the solar cell is made, it is made in this fashion. Let's say you take some silicon chunk. Let's say this is P type, and you deposit another material. Let's say this is N type, and then you have a depletion region in this particular fashion, and the light is basically coming onto this material onto the top of the material. Okay, so this is the three-dimensional view of this solar cell. So you have this particular throughout. Then you make something like metallic contacts also, because you have to connect it. So you have to make metallic contacts. You have to make metallic contacts. Okay, but you have to ensure that these metal contacts, they can also absorb light. Okay, so most of the time these metal contacts should be at least transparent. That's why there are certain metal electrodes which are used in the fabrication of the solar cell, something called as ITO electrodes or something like that. But why is that the case? Because if they are metals are mostly reflective. If they are reflective, then whatever light is falling onto the material, that is going to get reflected. And also they are occupying the area of the solar cell. You don't want them to occupy much area. That's why mostly you see that those metallic lines are made in a thin strips over the solar cell, so that the efficiency should be maximum and most of the light should fall on the top of the surface. Okay, that is the fundamental thing about it. And now what you have is that, let's talk about uh, let's talk about hmm, how much time is left. Oh God, it's 7:30 already. Can we finish this? Yeah, why this is I think it's a question. Do you have a question? Okay, why n-type is made thinner? Okay, you have the question in earlier for versions also. Okay, this is basically because what we want is that whenever, let's say, a p-type or an n-type, if you have a depletion region here, if let's assume for example you have the p-type on the top side of the solar cell. This is the top side. This is the top side where the light is coming. Okay, you want, whenever the electron hole pairs will be generated, they will be generated throughout the system. Okay. Now, let's not talk about throughout the system. In this case, most of the light will be most of the light and most of the light will be absorbed in this particular region only. And because it depends upon exponential decay, you saw from the Beer-Lambert's law, e to the power minus alpha x. Now it will depend upon how much is this x, how much is the alpha, and alpha is determined by the band gap, and as well as how much is the doping concentration of this particular region, which is the Na. Okay, so what controls that is basically if you have the electron hole pair generation in this region, then they should be basically separated. Okay, this should go here. This should go into the external circuit, which is the resistor load. So if it happens that if this, let's say I draw a p side here. Let's say I draw a p side here onto which the light was irradiating. If it happens that p side is very large, then whenever the electrons and holes will be generated, they will recombine before going into this region. Okay, you won't be able to collect those you won't be able to separate those electron and holes. So that is why the necessary the length of the p side and as well as the even the length of the n side, they are both necessary quantities in determining the efficiency of the solar cell. But most of the time, whenever it's about the top layer of the solar cell, whatever is the top layer of the solar cell, it determines that it has to be definitely thin. Okay, so it has to be thin. This has to be thin. Let's say this is p type here. Let's say this is n type. This has to be thin. Why? First of all, because we want most of the light to create electron hole pairs near the depletion region. If this is depletion region, we want most of the light to enter the depletion region. That is the exact way. And when we will be successful in doing that, we will be successful if this p layer is of the order of few nanometers or maybe few micrometers, so that light can at least enter. Because whenever the light will enter this region, it will exponentially drop, decay, e to the power minus alpha times z, where this coordinate is z here. Okay, so that it can create electron hole pairs. If let's say the p region is made thick, if let's say the p region is made thick, let's say p region is like this thick, this is p type, a light will come, it will enter, but it will exponentially decay up to this point only. This will be the this will be the absorption depth 1 by alpha. Then you see that most of the electron and hole pairs will be created here, but there is nothing to separate them. What will separate them? Because the depletion region is present in this region. So it will so happen that these electron hole pairs will get wasted, they will get recombined, and they have nothing, no role to play in the solar cell, in developing generating the current. So that's why you have to ensure that the region is thin enough so that most of the light gets penetrated, though most of the light creates electron hole pair just near the depletion region, so that it can separate it. Because this particular region is of the importance, because it only this particular thing has built-in electric field. In solar cell, you don't have external field applied so that it can separate it. Okay, so that's why it's necessary. Now what nowadays what people basically do is that they use multiple layers of different materials with different band gaps, like this, something called as maybe you might have heard, this is something called as tandem solar cells. Okay, so they use it because you will have a structure like this here, structure like this. Okay, so these are very thin structures of the order of nanometers. Okay, so that whenever the, let's say, electron hole pair gets generated, they fall into this region. Then maybe there is, I should say, they give rise to the external current in the form of the separation of the electrons and hole pairs, and you have to control basically the widths of these regions. But that's a different engineering perspective, how you make the tandem solar cells. But if you are more interested, you can learn about how tandem solar cells are made. But this is the exact reason of why these regions are made particularly thin. Okay, but let's dive into the question answer session. We cannot cover these things here. Okay, this is done. This is done. What else is remaining? Okay, let's talk about the question answer session. Maybe most of the things will get clear in that. Okay, this is done. Okay, yeah, let's talk about question answer. This we will talk about later. This is basically I wanted to show the overall schematic of where the optical systems are used in the communication and whatever you have studied from the, but you have only studied till now, you have studied the photodiodes, you have not studied the laser yet, but let's talk it about in the last lecture maybe. Okay, so let's directly jump onto the questions first. So this is about the Beer-Lambert's law, which we talked about. So this is about the Beer-Lambert's law, that the intensity basically drops as exponential of the into the particular in the particular direction or into the particular thickness of that particular material. So what you have to do, you have to consider a silicon slab of 5 micrometer thickness, and you have to determine the percentage of photon energy that will pass through the slab if the photon wavelength of 800 nanometer is used. And you have to take the absorption coefficient as this at 800 nanometer wavelength. Okay, so they have also given a hint that you have to use the Beer-Lambert's law. So you know that this is the Beer-Lambert's law. Now, how do you compute the percentage of, I should say, photon energy? How much photon, what you have to compute is the how much the percentage of photon energy that will pass through the silicon slab. So if it's a slab, if this is 5 micrometer, then there is some input light, then you have to compute how much will transmit. That is basically what is meant by how much is passed through the silicon sample. Okay, so you can write it basically as I over I naught is basically e to the power minus alpha z, where this direction is z here. Okay, then you can write the photon percentage of photons transmitted, because that's what you have to compute, will pass through. That will be I over I naught times the 100%. Okay, and this is basically approximately e to the power minus alpha times z times 100%. And you can solve this particular thing. Your alpha is given, z is also given. So I think this will be e to the power minus, how much is this? Alpha is 10 to the power minus 10 to the power 3 per centimeter. And z is approximately how much? 5 micron. You have to convert micron into centimeter. That will be 5 into 10 to the power minus 4. And you will approximately get e to the power minus 5 into 10 to the power minus 1, which will be e to the power minus 0.5 into 100%. So this will be 1 by e 1 by under root of e, and you will approximately get 60% of this as the answer. So I think you will get something like 60 point some percent, also 60 point something after the decimals. But that is the exact answer of this question. So this is the exact percentage of the transmitted photons. Okay, so it doesn't matter whether they have asked the percentage of photon energy, but intensity is related to energy. That's what I talked about, because intensity is related to energy per unit area. It's basically energy per unit area per unit time. Maybe I might have written in the previously, I said it's energy per unit area. It's actually energy per unit area per unit time. That's why the unit of intensity is watt per meter square. Yes. Actually, there is another quantity called as fluence. Fluence is basically energy per unit area, and the unit of this is joule per meter square. So just to rectify previously, maybe there might be some error in my previous discussion. So if you have if you have the intensity is given, then the energy can be correlated with it. So it doesn't matter. Okay, so that is problem number one. So problem number two is you have to consider the gallium arsenide, which is another, it's a 3,5 semiconductor. 3,5 means it has the element of group 3 in the periodic table, which is gallium. It has the element of group 5 in the periodic table, which is arsenide. So these 3,5 semiconductors are quite nowadays used in LEDs, for making lasers, for making photodetectors, and so on and so forth. Because most of them are direct band gap semiconductors. And that is the advantage we talked about. They have definitely the advantage that they don't cause much losses, okay, in the system. So you have a gallium arsenide. This is the gallium arsenide, and the thickness is being given as 10 micrometer, and temperature is 300 Kelvin, and photon intensity is given watt per centimeter square. Look, this is intensity. Intensity is energy per unit area, which is given as 0.05 watt per centimeter square. You have to keep, you have to remember, you have to be cautious about these units because they mostly play with these units in the examination. And the wavelength has been given as 793 nanometers. So it's incident on the sample. If the absorption coefficient is being given 10 to the power 4 per centimeter, and excess, let me just cross it. At excess minority carrier lifetime, we have not talked about this, but we have talked about it in the previous sessions. So whenever any, let's say this gallium arsenide will be having some electron intrinsic concentration. Okay, so whenever anything generation happens inside the system, you always have generation and you have the recombination in the system. Because of it, generation is basically the change in the electron concentration or the hole concentration divided by the lifetime of the carrier. So if it's n-type, if it is p-type, you can write it as delta p over tau. Okay. Similarly, you can write it in the for the recombination also. Okay. This is basically the generation rate, and you know it comes in the diffusion equation, that rate equation which you studied before, which is the dn d square n by dx square plus generation minus recombination. This is the rate equation. This is the exact equation which you need to solve in order to understand the electron hole generation and recombination and their I should say carrier kinetics. Whatever is happening in time and space in the sample, so that you have to understand using this equation. So whenever you irradiate a material with light, let's say this is light, there are electrons and holes generated, and they are generated in this fashion. Depends upon the material, definitely. But most of the time, the solution is like this, a Gaussian distribution. And as they diffuse, then it reduces in size, and it goes back to the background concentration. That is the exact scenario, and that comes because of the solution of this diffusion equation. Okay, so this generation component here is basically the change in this concentration divided by the recombination time. Okay, and you know that overall n dash is equivalent to the background concentration plus I should say the overall n is basically n naught plus delta n, which is the overall n in the system. This is because of the generation from the light. This is because of the background concentration. Okay, so this is the overall n. Now, now what you have to compute in this, the steady state excess carrier concentration due to incident photon intensity is. You see this word steady state, it is very important. Steady state means this equation you have to solve at steady state. What is steady state? You have to wait for a long time after hitting it with the light, so that system can at least get to a stable value. You don't have to study transient. It's like this. This is the output. This is time. When the light hits it at this particular point, light comes, the output starts to rise like this. It oscillates about a value and then it gets stable. This particular region is called as transient. This particular region is called as steady state. This is transient. This is steady state. And in the steady state, output almost stabilizes with time. If you want to study transient, then you have to solve this equation without considering the dn by dt term as zero. But if you want to study steady state, then you have to consider the dn by dt term as zero. That is this region. There is no change in the output with respect to time in the steady state. And if you And this simplifies the problem in steady state. If dn by dt is 0, you can directly write dn d square n by dx square plus generation minus the recombination is equivalent to 0. Okay, then you directly have the solution for these equations. But this is just the intuition I'm giving you, how you need to solve these equations. But what is asked in this question? The steady state excess carrier concentration due to incident photon intensity. Okay, you need to find the excess carrier concentration. Now, you know that there will be electron hole pairs generated, which will be equivalent to change in concentration divided by the recombination, minority lifetime of that particular carrier. Okay, excess minority lifetime. And you need to find this particular thing, which is delta, and it will be generation times the tau. So this generation, it can be written as alpha times the intensity divided by h nu, which is basically the generation is basically the intensity of the input light. Alpha, why this alpha is because it determines how much is absorbed in the system divided by the light energy. This is the overall generation rate for the I should say the generation of the electron hole pairs inside the system. So if you want to solve it, this is multiplied with tau. You can pretty much solve it using this particular system, using this particular values given in the system. The alpha is given, intensity is given, h nu is also given. So you should approximately get 2 into 10 to the power 14 per centimeter cube, which is basically this particular value. Okay, so now let me just recap what whether I have talked about these correctly. So yes, okay. Hmm, okay, fine. So now let's move on to this question. The solar cell is an example of, it's a very straightforward question, that it's an example of photovoltaics. What is a photovoltaic? What is a let's say thermoelectric? These are different types of devices which give rise to different uh, processes because of the photons, because of the input photons. Just like photovoltaics gives rise to voltage because of the photons, and photothermo gives rise to some thermal generation and thermal current, and it's used mainly as a thermal detector. And the thermal energy basically can even cause the generation of the electron hole pairs. So it is the photothermoelectric, and it can be used as an thermal sensor also. And then there is phototransistor. You don't need to know about these particular things here, phototransistor and other things. It is the transistor basically used along with the light. That is the fancy name for it. And bolometer is basically a photodetector. It's the photodetector. It's used to detect the photons, but of very low intensity, maybe a few photons. And that's why it's mostly used to detect something called as single photons. That's not a topic of concern in this particular right now. Okay, so what's written in this particular field? Okay, let's move on to the next question. And the next question is again, a bar of silicon is doped with a boron. You have a bar of silicon, and you have a bar of silicon. It's doped with boron. And what type of impurity is boron? I guess it is p-type impurity. So it's doped with p-type. That means it's Na acceptor type impurity. Okay. It is exposed to light such that electron hole pairs are generated through the volume of the bar at the rate. So it is exposed, the light is exposed to this particular system throughout the volume, and the generation rate is basically 10 to the power 20 per centimeter cube per second. This is the unit of generation. It is number per unit volume per second, per unit volume per time. Okay, this is the generation rate which is given. It's the rate. And the recombination lifetime is also given, which is what is 10 microseconds. Okay. Now what you have to find is the whole carrier concentration. So it's again quite simple, because whatever when the light will be irradiated, we are assuming that equal number of electron hole pairs are generated, and whatever will be the all of the photons are giving rise to electrons. That means one photon gives rise to one electron hole pair. That is the assumption. And so you can compute as generation as delta n divided by tau. You have to compute delta n. Basically, you have to compute delta p, but because delta n will be equivalent to delta p, so this will be equivalent to g times the tau. And generation is given, how much is it? 10 to the power 20 per centimeter cube into tau is how much? 10 microseconds. 10 into 10 to the power minus 6. So this is approximately 10 to the power 15 per centimeter cube. So this is delta n, which is delta p, equal number of electron hole pairs. But now what you have to find is the overall hole concentration. So that will be delta P will be basically the overall hole concentration, will be equivalent to background concentration plus change in concentration. Whenever there was a bar, its background concentration was some P naught. But if you irradiate it with light here, the concentration increased here, and this concentration change is delta P. So overall P dash will be equivalent to P naught plus delta P. So this is what is it basically signifies this. So P naught is basically given, it is 10 to the power 15 plus you found the delta P, which is 10 to the power 15. You get P dash to be equivalent to 2 into 10 to the power 15 per centimeter cube. So this is the exact overall hole concentration in this particular system. Okay, this is the answer of this question. So most of the people, what they do a mistake that they just stop here and they write 10 to the power 15 as answer, which is this one. And it will be an option in the examination definitely. But they don't think that the overall hole concentration will be the background concentration plus what is generated. Okay, so you have to keep this in mind always. Okay, now let me just have a few sips of water. God. Okay, so now moving on to the question number five. In question number five, it's about the solar cell, and it's about maybe the curve which we talked about. You need to increase the area under this particular curve, which is the fill factor. Okay, so you have to consider the p-n junction solar cell with an area of this at this particular temperature, and this has an optical absorption coefficient of given, and reverse saturation current, which is I naught, that is 7 picoamps, and the photo current is given as 1 amps. Okay, that means you have a solar cell. This is P, this is N, this is the external load. Okay, this is the external load, and you have to compute the maximum output power if the fill factor is 0.75. So fill factor is given, that is 0.75, and the fill factor is basically VMIM divided by V open circuit into short circuit current. So this is basically equivalent to 0.75. Okay, and remember this particular thing here is the power generated from the solar cell. This is the output power. So you can write the output power to be equivalent to basically, let me drop this. Let me just let's first calculate what you need to find is the output power. Okay, so you need to find the overall. Okay, just let me drop this. You need to first of all evaluate the this particular thing. But how do you evaluate this thing? This is the output power of the solar cell. This is the output power of the solar cell. That means VMIM can be written as fill factor times the VOC, open circuit voltage, into short circuit current. What information is given? Open circuit voltage is unknown, and we need to compute the short circuit current also. But that is I think is given in this question. Yeah, photocurrent, that is the 1 amps, the short circuit current, which is the photocurrent. Okay, so we need to find VOC. How we are going to obtain the VOC is basically KT by Q ln of 1 plus IL divided by I short circuit. Okay, let me rub this. So VOC is KT by Q ln of 1 plus IL divided by I short IS, which is the reverse saturation current. Let's write it I naught. This exactly comes from the diode equation. There's no need to remember this. Basically comes from this equation, e to the power I naught e to the power qv by kt minus 1. Okay, so you need to find it under open circuit voltage. In open circuit voltage, IT will be equivalent to 0. So you can obtain the voltage from this particular thing. Okay, that is the overall thing. So now open circuit voltage you can compute. You have to. It is mentioned that it's at 300 Kelvin, which is room temperature. So you can take KT as 0.026, and I guess other things are given. So ln of 1 plus how much is IL? It's 1 amps. Is it 1 amps? Okay, yes, it's 1 amps divided by 7 picoamps. You see that this value is huge. This value is so small that when you bring it to the numerator, it will become, let's say, it will become of the order of 10 to the power minus 12 is pico. So it will when it will go to the numerator, it will become 10 to the power 12. So you will get VOC as 0.026 times the ln of 1 plus 10 to the power 12. So you can ignore 1 here, and this is approximately ln of 10 to the power 12. Okay, and this is 0.026 ln of 10 to the power 12. You can write 0.026 12 ln of 10. Using the properties, you can write 0.026 into 12 into ln of this particular thing is 1, and when you evaluate this you will get the open circuit voltage to be equal to 0.667 volts. I think 0.66 volts is enough. Yes, 0.66 volts as the open circuit voltage, and it will be required here in order to evaluate the VMIM, which is the output power. So the output power will be fill factor times the VOC times ISC. So fill factor will be 0.0. No, the fill factor is I think given. It is 0.75 into 0.66 into 1. So output power will be approximately equal to 0.5 watts. So that is the particular answer of this question. Okay, so now moving on to the next problem. Problem number 6. A photodiode has a responsivity. Now this is about the photodiode. Maybe I have not mentioned clearly about the photodiode, but what is its responsivity? Basically, there are many parameters of a photodiode. It's used to detect the photons, or count the number of photons, detect the photons, or detect its intensity. If you have a photodiode like this, if there's an input beam coming, with the help of photodiode, you can compute intensity of light, you can compute number of photons of light inside the present in the light, you can compute the flux of the light. Okay, you can compute the energy, you can compute the power. These are the parameters. You can compute the responsivity of a photodiode is its internal parameter. Responsivity basically is current divided by the input power. So it's the current or the output produced by the it's not output. It's the output produced by the photodetector in the form of a current divided by the input power, which is the light. That is basically the responsivity. And if you want to write responsivity in a more clear way, you can write it in the form of the efficiency. You can write responsivity in the form of efficiency divided by energy of the particular photons. Okay, so what you have to find here is, let me just clear this out. Let me just clear it. Why is this messed up? Let me just clear this. So you have to find the efficiency of a detector. So you know that responsivity is basically efficiency times the energy of photons. You can write it as efficiency times hc over lambda, and maybe there is an e factor here, which is because of the charge factor. You can find the efficiency as efficiency will be approximately equivalent to uh, what it'll be hc over lambda times the, you can write it as responsivity times the E, okay, and divided by the electronic charge. You can write it responsivity times the hc over lambda times E. So you need to evaluate it, and you need to first of all evaluate hc by lambda from here. And I think this will be approximately maybe 2.3 electron volts. Then you can use this particular value, and other things are have been given. What is given? Responsivity is given 0.25, and you can multiply simply 0.25 multiplied by 2.33, which will give you approximately 0.5, 0.5, yeah, 0.5 as the value of the as the value of the this particular efficiency of the efficiency of the detector. But the 0.5 has to be multiplied with 100%. So it will approximately give you 50% or somewhat near that. So this is the nearest of the value. Maybe you need to compute it. You might get somewhat like 0.58 as the answer of this question. And the nearest value is basically 58. So that is the exact efficiency of this particular detector. And now efficiency is basically uh, there are two efficiencies. The first is, I want to talk about it a little bit. The efficiency of a detector, there are basically two efficiencies. One is internal efficiency, something called as internal quantum efficiency. Other is external efficiency, something called as external quantum efficiency. External efficiency is how efficiently you take out electron hole pairs. Internal efficiency is how efficiently electron hole pairs get generated internally. Okay, these are the two efficiencies which are mostly confused in the literature, even in the books. So this is the internal thing of a detector. It's a material characteristics. External quantum efficiency is also material characteristics, but it depends upon how efficiently you are extracting those electron hole pairs. Internal quantum efficiency is how much light is getting converted to the or how many electron hole pairs are at first getting generated by the inside the material. Now, once they are generated, now you can separate them. But how well you are separating them, that determines the external quantum efficiency of the photodetector. Okay, let's say you have a photodetector and you have generated electrons and holes here. You have generated electrons and holes. But now, if so many electrons and holes are generated, but if you are able to take out few electrons and holes, that means your external quantum efficiency is low and internal quantum efficiency is high. But if at a first position you are not able to generate that many electron hole pairs, that means your internal quantum efficiency is low, and then it is directly going to affect the external quantum efficiency as well. Okay, so this is the general concept of it. I think my pencil has to be charged for a few seconds. Let me just talk about this later on. Let me just talk about this quickly. What is question 7? Now, moving on to the question 7, you have a silicon photocell which has a dimension of 4 centimeter cross 4 centimeter at 300 kelvins, and it's being tested, and the efficiency is 100%. Okay, which is not which is a very unrealistic value. Initially, the cell is kept in the dark. The current value is given as the current flowing because of the light is 10 microamps. It's forced through it in the direction of a good conduction. The voltage across the diode is open circuit voltage. The reverse saturation current you need to evaluate. Again, that particular equation will come to rescue. I guess it can be solved by using that. If you have the open circuit voltage to be equivalent to KT by Q, ln of maybe 1 plus the light current divided by reverse saturation current, then what you need to find is the reverse saturation current. Just bring it here. You can write IL divided by reverse saturation current is e to the power V open circuit voltage Q times V open circuit voltage divided by KT minus 1. So you can write reverse saturation voltage to be equivalent to light current e to the power minus QVOC divided by KT. And we are neglecting this particular minus one here. And what you can do is that this everything is given. This is 100 microamps e to the power minus 0.466. Is this a value? Yes, 0.466 divided by into electronic charge divided by kT, which is 0.026. And you will find that you will get approximately 1.6 into 10 to the power minus 12 amps, which is approximately 1.65 picoampere of the reverse saturation current. 1.65 is the closest. So this is the answer of this question. So you see the reverse saturation current is very small, of the order of picoamps. That's what actually makes sense inside this particular solar cell. Okay, rather it's a photo cell, not a solar cell, to be precise. Don't confuse it with it. And in many of the order of magnitude, what is this? Okay, let's leave this. Okay, now what is the PN photodiode can be used as a better photodetector than the PN diode. And the intrinsic region width in the PIN diode is much larger than the space charge width in the normal PN diode. If the reverse bias is applied to the PIN junction, the space charge region extends completely through the intrinsic region and has no electron hole recombination. Okay, so there is a modification of a PN diode, which is something called as PIN diode. In PIN diode, you have a P region, you have an N region, and you have an intrinsic region here. No doping. Because of that, most of the depletion region is inside the intrinsic region, because you know that depletion region is penetrated more towards that region which is lightly doped. Now, if you don't have any doping at all, just like an intrinsic, then most of the depletion region will be towards the intrinsic region. Okay, that is the exact concept. And what happens basically is that intrinsic region, the width in the PIN photodiode is much larger than the space charge width in the the statement is saying that PIN photodiode can be used as a better photo detector than a PN diode. And the statement 2 is saying if the reverse bias is applied to PIN junction, the space charge region extends completely through the intrinsic region. So whenever you apply a reverse bias to this particular system, so what is going to happen? There will be, first of all, there will be depletion region here. There will be depletion region here. There will be depletion region in this particular side. There will be depletion region at this particular region. So you see that whenever you will apply this particular reverse bias increases the depletion width. And whenever depletion width will increase, it will totally occupy this particular intrinsic region. And that is better. That's what we want. The more the depletion width region, the better will be the photo detecting response, because better you will be able to, I should say, move those electron hole pairs. So that is the exact reason that why PIN diode acts as a better photo detector than the PN diode, because in the PN diode the width can be increased, but what happens is that you don't have absolute control over making the entire region as a depletion region. If you have the entire region as a depletion region, that is one of the best way to I should say separate electron hole pairs, because you know that there will be internal electric field present in it, and that internal electric field can basically result in the I should say they can give rise to the separation of the electron hole pairs. So this both of the statements are correct, and they are basically I should say supporting each other. And that means if the reverse bias is applying, the space charge region extends completely through the intrinsic region and has no electron hole pair recombination. So that's what basically is meant, that it will prevent the electron hole pair recombination. So let me show it like this. If this is P, this is N, this is intrinsic, so you'll be having positive in this side, negative on this side, and this will give a negative, this will give rise to positive. Okay, yeah, this is the intrinsic region. So remember that here is Na doping, you have Nd doping here, and there is no doping here. So even this particular depletion region will be more penetrated towards the lightly doped region. Even there is no doping, then it will be more penetrated towards the intrinsic region. So that's the fundamental thing of why Pi N diode is mostly used. And if you will draw a band diagram of it, that is also a little bit tricky, because this is P, this will be N, and in the middle, this is like this, intrinsic Fermi level is in the middle, which is the intrinsic level. So whenever you combine it, you see that there will be step like figure in the equilibrium. Just like if you, whenever you connect it, all of the Fermi levels will want to be aligned. If you have the aligned Fermi level, then this will be the P type, this will be the P type, this will be the N type, this will be the N type, and intrinsic has to be somewhat like this, somewhere like here. Then you have to draw it like this, then you have to draw it like this. This is the exact band diagram of the PIN structure. So these slopes are basically necessary in order to separate the electron hole pairs. That's why I told you that combination of different layers of materials are necessary, because they give rise to internal electric fields, and internal electric fields will give rise to separation of the electron hole pairs. And you see that here this is P type, this is N type, and in the intrinsic it will be exactly in the middle, at least at equilibrium. Non-equilibrium scenario is different. In non-equilibrium, you get the quasi-Fermi levels. So whenever you have a silicon, which is, let's talk about N-type silicon, this is EF, this is Fermi level of the N-type silicon. If you irradiate with light, you generate electron hole pairs, electrons, holes, and because of the generation of electron hole pair, now this system has two different Fermi levels now. It has a electron Fermi level, it has a hole Fermi level, because this system is now a non-equilibrium system. It's not in equilibrium. This system is in equilibrium. You're not disturbing this system, but when you disturb the system, you have created two different Fermi levels in that system, which are represented as quasi-Fermi levels. Quasi-Fermi levels. Okay, so now you have to deal with electron Fermi level and whole quasi-Fermi level separately in the non-equilibrium. Okay, and now moving on to the next question. Okay, so this was asked in GATE 2016, so it has to be a special problem, I guess. So the figure shows IV characteristic of a solar cell illuminated uniformly with solar light power. Okay, so there is a solar cell and it has been uniformly illuminated. Uniformly illuminated means illumination throughout the sample. Okay, uniformly. There is no high, low illumination at any point. Uniform illumination. Whatever is illumination here, it is same at all the points. And this is the solar light power given. That means this is the input power. The solar cell has an area of 3 centimeter square. That means this is 3 centimeter. This is 3 centimeter. And the field factor is given, which is 0.7. We have to find the maximum efficiency of the device. Okay, now it is related to the previous concepts we talked about. We know that field factor is basically VM IM divided by VOC I short circuit. So this is the output power. This means it is the output power divided by VOC ISC. This is the field factor. Now, what you need to find is efficiency. Efficiency is output power by input power into 100%. And you can write output power as, from this you can write output power as fill factor VOC ISC divided by input power into 100. Everything is given, I guess. Fill factor is zero point 0.7, VOC is 0.5. This is VOC. ISC is 180 into 10 to the power minus 3 amps. Okay, and divided by input power is given as 100 milliwatts, 100 milliwatts per centimeter square. So you can write 100 milliwatts per centimeter square. Just note to make sure these all units are in meter or either centimeter into 100. So when you solve this, you get the efficiency to be approximately equivalent to 21%. And this is the exact answer of this question. And what else is required in this question? Oh, yes, there is a trick here. This is the power actually is power. Whatever the input power is, you have to multiply it with the area because we usually write power as power per unit area. But then you have to multiply the input power with respect to the overall area. So it will be 100 milliwatts into 3. So it will be 0.3 watt. Okay, because this is not the input power. This is power per unit area. Okay, this is power per unit area is 100 milliwatts per centimeter square. So the power will be 100 milliwatts per centimeter square multiplied with the area. So you will get it approximately 0.3 watts, which is the input power. So now this input power has to be used here, 0.3 watts. Watts. So this is going to give you 21% efficiency. This is the exact answer of this question. We have to hurry because my Apple Pencil is getting fully uh, drained. Just let it charge for a few seconds. Again, a question about these questions are asked a lot of times in the gate about the fill factor efficiency of a solar cell because that's what people are mostly talking about, efficiency of a solar cell. So let's quickly jump into this question. What we have to find, we are given the area of solar cell. Again, this particular illumination uniformly 100 milliwatt per centimeter square, which is the power per unit area, has been given as 100 milliwatts per centimeter square. Efficiency is given as 15%. VOC is given as 0.7 volt. Fill factor is given 0.8. Even the thickness is given as 200 micrometer. I don't know whether the thickness will be used. Okay, 200 micrometer. The average optical generation. We have to find the generation rate. We have to find G. Okay. Now let's talk about what information we have. Fill factor is given. Let's say uh, fill factor is output power divided by VOC ISC. Okay, you can write what do we need for the first of all, what do we need for generation rate? Generation rate can be written as delta n divided by what is delta n divided by t, but you don't have any information about delta n and t. How are you going to compute it? You know that the you know that overall current can be written as the charge divided by charge per unit time. Then basically you can convert overall this particular generation rate into something like current divided by charge per unit volume. So I hope this will give you the correct thing. Yeah, this will give the correct thing. Okay, I by Q divided by per unit volume. Yeah, per unit volume because of delta N has to be there. That means the generation rate will be current per volume per I divided by Q into volume. Now this is I short circuit current. Now that is what you're going to get from the fill factor. So I short circuit current will be exactly equivalent to efficiency, not the efficiency, it will be fill factor. Oh God, it will be output power divided by fill factor into VOC. So output power by input power is basically efficiency. So efficiency is given, efficiency times input power will be output power. So output power you can write efficiency times the input power divided by fill factor times the VOC. Everything is given, I guess. This is 0.15, that is 15% into 0.1 divided by fill factor is 0.8, VOC is 0.7. So you have the short circuit current to be approximately 0.026 amps. Okay, now this has to be put into the generation equation, which is 0.026 divided by 1.6 into 10 to the power minus 19, the electronic charge times the volume. Now the volume is area times the thickness. The area is how much? Is it one centimeter square times the thickness? I thought thickness won't be used, but it is times the times 200 micrometers. That is 0.02. Yeah, 0.02. This is all in centimeters. So you have to multiply it and you get approximately 8.3 into 10 to the power 18 per centimeter cube per second as the generation rate. 8.3, okay, 8.3, okay, 8.4 is the correct answer. Maybe there is a multiplication error, but this is the exact answer of this question. Into 10 to the power 18, the order has to be definitely correct. You get the 10 to the power 18. All right, so, okay, what is this? Okay, this is again the same thing. This is the normal diode operation. This is the photodiode operation, photodetector, uh, and this is the solar cell operation. I think this has been covered quite clearly by professor also in the class. I just wanted to discuss few things which aren't mentioned in the class. Okay, so I think we are done with today's session. We have solved these particular problems, and I think we have overshooted the time also. Okay, what is irradiance and how this unit comes up? Okay, I will just briefly talk about it because I won't be able to draw anything. My pencil is down fully. It's drained. So basically, I was talking about irradiance is basically irradiance. If you see the units, it's watt per meter square per micrometer. This is per wavelength actually here, not any dimension of the space dimension. It's not the space dimension. It's the per wavelength. Whenever you draw the irradiance. Maybe I confused it a little bit there. Whenever you write irradiance here, you write watt per meter square per micrometer. Micrometer. This is just like you normalize it with respect to at every wavelength. This micrometer is because of the wavelength. This and watt per meter square is intensity. It's like intensity per wavelength. At each wavelength, what is the intensity of the light which is coming out? That is what is irradiance. That's why this unit is normalized with respect to wavelength at each particular value, at each wavelength value. Okay, that is what is the basically a unit of the irradiance. Don't get confused that this micrometer is the space dimension. It's the wavelength of the particular light at this particular different wavelengths. You normalize the overall intensity with respect to the wavelength, and the unit comes up to be something like this. Okay, and if you don't normalize it, then you won't be getting this particular curve. You have to definitely normalize it because intensity at different wavelengths will be different. Whenever you have different intensity values at any different points, let's say you have a y versus x. Whenever you have some curve which has different values of y at different values of x, I should say in terms of the amplitude taken at different, I should say different other third variable, then you normalize this particular variable with respect to the x variable in order to make a smooth transition, smooth curve. This is called as normalizing. This is the similar thing. You have the irradiance as the intensity per wavelength. So at each wavelength, what is the intensity? That is gives you the irradiance. And intensity we talked about is energy per unit area per unit time. Okay. Now this area information is embedded in the intensity itself. This is the area of the beam of this overall beam of over which the of the overall I should say area of the irradiated region that gets embedded in the intensity information. Okay, and but this information is here the wavelength information. That is what the spectral irradiance is. That's why there is a word spectral. Why is there a word spectral? Spectral means associated with light. It's the irradiance associated with each spectral component. Spectral means Spectral basically indicates some frequency information. Frequency information means some wavelength information also. That's what the spectrum even is. A spectrum word indicates basically. Spectral. Okay, I hope that answers the question briefly. But now we're going to stop the session because I won't be able to draw anything like that. I hope you got the answer. I won't be able to write anything. My pencil is down and okay. So we'll be ending this session. Okay, fine. Thank you. So I'll be ending this session now, and we will meet in the final session. Maybe I think, is there any final session also, or this is the last session of this course? I'm not sure. I think there is a final session. Okay, let me just first of all